Hi everybody, and welcome to the second day where we're going to be looking at describing features of functions by looking at the derivative. Now today we're going to be looking at something called concavity. We already briefly talked about concavity in the previous chapter, and we know that concavity is the curvature of the graph. When a graph is concave up, we say it looks like a cup. But sometimes only portions of a graph are concave up, and some portions of the graph are concave down. Now, concave up we define as places where the second derivative of x is greater than 0. You'll notice that unlike increasing and decreasing, this is just greater than and not greater than or equal to. What that means is when we write our intervals, we're only going to be looking for places where we're not including the endpoints. Okay, so if I'm looking at the original graph, which, by the way, this is never going to be a thing you have to figure out because you're going to have to estimate here, but we just wanted to show you what this really looks like in the original graph. The original graph is concave up whenever it's curving up like a cup. Now you can imagine this cubic graph as being made of two different pieces. A part of it that curves down, which would be concave down, and part of it that curves up, which would be concave up. So we would say that the concave up part starts here and goes like this. Now I'm estimating where it starts as being x is 1. We don't know exactly, but it's pretty good guess that it's probably about halfway in between this peak and this valley. So if I said, where is this graph concave up, you would say from about 1 to infinity. And the reason you would say is because f double prime of x is greater than 0. Now you'll notice I made this in open parentheses because concave up is always going to use open parentheses. Now, if I'm looking at the derivative, which by the way, this is the more likely situation, is that you have the derivative to look at. When you're looking at the derivative, the second derivative is really the slope of this graph. So because we're already starting with the first derivative, the second derivative would be the slope of what you're looking at. So we would look for where the slope of this graph is greater than 0. In other words, we would look for where this graph is going uphill. So unlike before where we were focused on are we above or below the x-axis, now we're looking at the slope. Since this slope is going uphill, we would say that the original graph was concave up from 1 to infinity because f prime of x, the graph that I have, it has a positive slope. So since the derivative has a positive slope, the second derivative must be greater than 0. Now since concavity is focused on the second derivative, we're going to find the second derivative of our function if we have one. So the first derivative would be 6x squared minus 12x, which means the second derivative would be 12x minus 12. Now we're going to make this equal to 0 to figure out where to divide up our chart. We're going to make a chart that's very similar to what we were looking at before. So we would factor out a 12, and we would get x equals 1. In our previous problems, we were making a chart of the signs of f prime, but here we're going to make a chart of the signs of f double prime. So I would start at negative infinity, then I would have 1, then positive infinity. Because there is no set interval that I'm working with here, it just goes from negative infinity to infinity. Now here I'm going to look at the second derivative. So I'm going to pick a number that's less than 1, I'm going to choose 0, and a number that's bigger than 1, I'm going to choose 2, and I'm going to plug them into this equation. So, if I plug in 0, 0 minus 1 is negative, which times 12 gives me a negative number, and 2 minus 1 is positive, which times 12 gives me a positive number. But unlike before, these are telling me about the concavity. So if I wanted to sketch a picture to help me visualize this, all of the positives would be shaped like a cup, and all of the negatives would be shaped like a frown pointing down. Which means if I were to say, where is your graph concave up? The original graph is concave up between 1 and infinity because the second derivative is greater than 0 there. Now, one thing I should point out, and this is really important, your answer should always reference what you have. So since here I have the first derivative, my answer should say, because the first derivative has a positive slope. I can't jump straight to just saying the second derivative is positive because I don't have the second derivative here. In this problem, however, the second derivative is something I was able to calculate, so I can jump straight to saying the second derivative is positive. Now let's talk about concave down. For concave down, we said you're going to look like a frown. So these are going to be places where the second derivative is less than 0, is negative. When we look at our graph, and again, this is not something you're ever going to have to do based on the original graph, but it is something we should just visualize. The original graph is concave down for that section. So we would say it's concave down between negative infinity and 1. And our reasoning, and we're never going to have to write this for this particular case, but it's good to focus on this, is because the second derivative is less than 0. Now, if we were looking at the derivative already, since the second derivative is the slope of this graph has a negative slope in this section right here. So the original function would be concave down between negative infinity and 1 because the derivative has a negative slope. So since the derivative has a negative slope, the original was concave down. Once again, for this one, you would start by doing the same work as above. Because you would start by finding the second derivative, making it equal to 0, and making this chart. After you have the chart, you would just choose the section where you were concave down instead of concave up. So we would say negative infinity, 1, because the second derivative is less than 0. Now, one last vocabulary word you should be familiar with is this idea of a point of inflection. A point of inflection is a place where the second derivative is equal to 0 or does not exist, but this is the really important part, and the concavity changes. So there are going to be times where your second derivative is equal to 0 or does not exist, but your concavity doesn't actually change there from positive to negative. In order to be a point of inflection, the concavity has to actually change. So it has to change from positive to negative or negative to positive. On this graph, the point of inflection would be here, because that's the place that links together this concave down portion of the graph with the concave up portion of the graph. So because the concavity changes from negative to positive, we would say x equals 1 is a point of inflection. For the next picture, the point of inflection is going to be the place where the slope changes from negative to positive, because the second derivative is the slope of the first derivative. So the slope changes signs here, which would be at x equals 1 again. And for our original function, it's the same work we did before. In our chart, we would find our derivative. We would make it equal, or we would find our second derivative. We would make it equal to 0. We would make this chart, and then we would ask ourselves, does the concavity actually change here? So we had a negative concavity. Afterwards, we have a positive concavity. So we would say x equals 1. All right, guys, thank you so much for watching, and I hope you have a great afternoon.